All right, guys, well, I'm going to go ahead and start explaining my response to the gallery walks, and really there's not a whole lot for me to go over this time. You guys did a very good job. Just a couple things for me to clarify, but let me walk through them individually. So let's start with problem number A here. Team 3 did this one. This is the neurological adaptations to resistance training. The only things I have to add here, well, there's really the four changes: the increased rate coding of motor units, synchronization of motor units, GTO changes, and muscle spindle changes. Only thing I'd add here on the increased rate coding is that we need to add in the calcium there, increased calcium because of the increased action potential, which that's what would lead to the increased actin myosin interactions. And then the one thing I'd add on the muscle spindle one is that that leads to a decrease in transition time between the loading and exploding phase during plyometric activity. So that's number one, or that's A. And then B is also resistance training, but more of the other factors related to hypertrophy. And so we have the genetic influence, myostatin, covered that one well. Hormonal influence, cortisol is the catabolic. We need to have that in the beginning, break down some tissue, and then we need to start building back up and switch over into anabolic. And so we see this with the testosterone, mostly in males, but then we also see this an increase in testosterone receptors in females, and that probably explains part of the response in females. And testosterone directly activates protein synthesis, as I said here. I'm going to use my laser pointer actually, and then testosterone directly activates satellite cells, and those satellite cells can either fuse into other cells to cause hypertrophy, or they can fuse together to cause hyperplasia. Okay, and so here's the part about women: increase in testosterone receptors. Okay, and then there's growth hormone. Growth hormone stimulated, the release of it stimulated by exercise and sleep. Um, its release and binding to the liver cause the release of IGF-1, and IGF-1 is actually what stimulates that growth. Then we see mTOR. mTOR is a very important molecular regulator that needs to be activated to cause hypertrophy. It gets activated by insulin, resistance training, and amino acids, specifically leucine, as this group said. Leucine is found in high quantities in whey protein. Estrogen may be important for females. Okay, and then this next part, the damage from exercise. Strain's a primary factor with muscle damage. We get satellite cell activation and proliferation, kind of already talked about that. The one part that they didn't say here is that the primary way to damage muscle or put extra strain on muscle is with eccentric contraction, so make sure you include that. Okay, endurance training here, the factors related to stroke volume. There's a few things that need to be kind of just reordered here. So first of all, we get the left ventricular chamber size increase. This is good. This is not necessarily due to hypertrophy of cardiac muscle, but it's more due to just widening of that chamber. Okay, the increase in plasma volume doesn't cause more preload, or isn't caused by more preload. It kind of goes the other way. The increase in plasma volume increases preload. Okay, and then the causes of that increase in plasma volume, this group had down here in E. So make sure you look at those, and those aren't the causes of increase. Red blood cell volume. Red blood cell volume increase is caused by this over here, hypoxia, lack of oxygen. That stimulates erythropoietin release, and then that stimulates red blood cell production. All right, so then so then after the red blood cell volume one, let's look at here at C. So this increase in cardiac contractility, we see that with increase in SNS activity, as this group said, especially at maximal exercise. And that would increase calcium release, and calcium sensitivity changes all throughout, not just at maximal exercise, but both submax and max. We see an increase in end diastolic volume, and that's partially due to the plasma volume that was mentioned before, but also partially due to heart rate being lower. That would only apply to submaximal exercise and resting. It doesn't apply to maximal exercise because heart rate doesn't change maximally. And then we have this increase in left ventricular wall thickness, not caused by these things mentioned here by this team, but caused by that cardiac myocyte hypertrophy. Okay, let's move on to D. This one has the tables, really. Okay, so let's talk about these submaximal exercise. Heart rate would decrease. That's due to the preload increase, all right, stroke volume increase. Glycogen use would decrease because glycogen is used in the glycolytic system, and our oxidative system becomes more powerful, so we don't need to use the glycolytic system as much. Fat usage goes up, again, because the oxidative system gets more powerful. Oxidative system goes up because we've got more mitochondria and all this other reasons in AVO2 difference. Lactate production goes down because of the increased glycolytic system, or because of the decreased glycolytic system usage and increased oxidative. Lactate removal goes down just simply because production goes up. VO2 would stay about the same. Epinephrine levels go down because exercise is less stressful at any given intensity. Sweating can go up because of those adaptations to heat we talked about. Ventilation goes down because exercise is not as hard and we don't have that same increase in CO2 because we have less activation of the glycolytic system. Stroke volume goes up because of all those changes we just talked about, and cardiac output can stay the same. Okay, this group mentioned the increase in PNS, which is true, but probably more importantly, we have a decrease in SNS. And how do these help us exercise longer? We got higher economy, less stress, more efficient, all of these things. Less use of glycogen is important for fatigue as well. And what about maximal exercise? No change in heart rate. It's not a trainable factor. Glycogen usage goes up maximally because we have a more powerful anaerobic system. Fat usage stays the same, primarily because we're not using any fat at maximal exercise, so it wouldn't change because we're not using any. Oxidative system activity is going to go up, more powerful. Lactate production goes up, lactate removal goes up because of that. We talked about those changes. Remember, lactate removal goes up because of the increased shuttles, increased circulation, increased Cori cycle enzymes. VO2 goes up because of that. All those changes to the Fick equation drives your VO2 max up. Sweating rate goes up, ventilation goes up because we're tapping into more of what the lungs were already ready to do. Stroke volume goes up like we already talked about. And because of that stroke volume increase, cardiac output can also go up. This is all great information here, but not necessarily necessary for this one. Those things are explained in other places. All right, team 6, prompt E, looking at the changes in AVO2 difference. Definitely due to a decrease in blood or oxygen in the veins, not a change in the arteries. This is due to the mitochondria getting more powerful, so we can extract more oxygen. This is due to fiber types becoming more oxidative, so going from type 2A to type 1 or type 2X to type 2A. Also type 1 fibers hypertrophy, which increases oxygen usage. We also have increased myoglobin, which is going to pull more oxygen out of the blood. Also have increased capillary density, which decreases diffusion distance here. Okay, increased CO2 production. This would occur along with heat production and decrease in pH because we're driving ourselves further, all right, pushing ourselves harder, and so that would shift the curve more to the right, which would cause more oxygen unloading, which would lead to more extraction of oxygen. Red blood cells, this is a nice description here talking about red blood cells and the overall increased ability to bring oxygen to the cells and extract oxygen. All right, prompt number F, team 5, changes due to the heat. There's the blood changes that take 2 to 3 days. This is plasma volume increase is what we're talking about, caused by increased plasma proteins, which increase osmotic pressure, as well as an increase in ADH and aldosterone. All of these lead to more plasma, more water in the blood. If we got more plasma volume, we get higher preload, which allows our heart rate to decrease, which allows us to keep the same cardiac output with less stress on the heart. Increased blood flow to the skin. And the plasma volume allows us to send more blood flow to the skin without sacrificing preload. And we see this with, and this also allows us to sweat more if we have more plasma and blood in the skin. Changes in sweat take about 2 weeks to do this completely. We start sweating earlier, we sweat more, we sweat in the arms and the legs, and our sweat's more diluted, and we get more blood flow to the skin. Okay, part of the reason how we sweat more is our sweat glands hypertrophy, a larger diameter of sweat glands. And yeah, so part of the reason that our sweat is more dilute is because that increased aldosterone sensitivity, which stimulates the sodium chloride pumps, which pulls the salt back from the sweat as it's passing through the gland. Also, the sympathetic nervous system activation will cause us to sweat more. And we already talked about the sweat gland hypertrophy. So if the body stays cooler, this will lead to lower SNS activity, and that'll decrease heart rate. All of these adaptations to sweating also allow us to stay cooler, which causes an increased evaporation or an increased or conduction and increased radiation, which helps us get rid of heat better. All right, and that's pretty much it for that one. And then the last one, prompt G, team 4 here, the altitude changes. They did leave out the chain of events that happens at altitude when you first get there. So you get to altitude, oxygen in your blood goes down. That stimulates an increase in ventilation. If your ventilation goes up, then your CO2 goes down. So you blow off CO2. That leads to a leftward shift of the curve. That leftward shift of the curve takes us down here to cause an increase in loading of oxygen, which does actually help our blood saturation a little bit. So that takes us back to here, and that increases our oxygen in the blood a little bit. So that's a helpful part of our body's reaction. But we also lose a lot of water at altitude because we breathe more, we lose water with that, and we urinate more, we lose water with that. Because of those things, our stroke volume goes down, which forces our heart rate to rise to adapt to that. And this will overall, acutely in the first couple of days, maybe cause a little bit of an increase in cardiac output. So that can help us a little bit. But long term, the stroke volume keeps going down a little bit. Heart rate can't make up for that. And so we get this overall decrease in stroke volume, which leads to an overall decrease in maximal cardiac output. And yeah, so we got that. And then down here, when we go back here first, and hemoglobin and hematocrit increases because of that decrease in partial pressure of oxygen. Body releases EPO from the kidneys, which causes more red blood cell production, and we increase hematocrit. Okay, and then we, because we just can't stimulate the mitochondria enough, we lose mitochondrial density, and then we lose oxidative capacity. Our capillary density goes up, the body's attempt to get more oxygen to the cells. Our muscle cells atrophy. So this is saying here, and that's due to loss of appetite and causes overall weight loss. All right, guys, so that does it. Good luck on the test.